Welcome back to AI.Code.Cast. When I was prepping for my first tech interview,
Oh, yeah?
there was this one problem that kept popping up. The combination sum problem.
Oh, yeah, that's a classic.
Yeah, it's a real classic, and today we're going to do a deep dive into it.
Awesome. It's a really great one to tackle.
Yeah.
Because it forces you to think, beyond brute force and get creative with your algorithms.
Right.
Plus, understanding it really helps you grasp the power of backtracking.
Okay, cool. So imagine
Yeah.
you're given a set of distinct numbers.
Yeah.
Let's say 2, 3, 6, and 7.
All right.
And your challenge is to find every single unique combination of these numbers that adds up to a specific target sum,
Gotcha.
which in this example, let's say is 7.
Okay, so our target is 7.
Yep.
And here's the catch. You can reuse numbers as many times as you need.
Okay.
So, for instance, a valid combination could be just 7 by itself.
Okay.
Or it could be 2 plus 2 plus 3.
Right.
Which also equals 7.
Exactly. Now, I remember when I first saw this, my brain went straight to brute force mode.
Yeah, I feel like that's everyone's first instinct.
Right. Just check every possible combination.
Yeah, you just want to get in there and try everything.
Yeah.
But think about it, as the set of numbers grows, the number of potential combinations just explodes.
Oh, okay.
It quickly becomes computationally very expensive, and your code's just going to be running for ages.
Yeah. So brute force is out.
Yeah, brute force is not the best way to go here.
So what's a smarter way to approach this? Give me a hint.
All right, so let's think about how we can explore these combinations systematically, but avoid unnecessary calculations. What if we could abandon a path the moment we realize it's not going to lead to the target sum?
So it's like we're walking through a maze, and if we hit a dead end, we immediately turn back.
Right. Exactly.
And try a different path.
That's the idea.
Okay.
That's the essence of backtracking. So we explore potential combinations, but the moment we overshoot the target sum, we backtrack and try a different branch.
Gotcha. Okay. I'm starting to see the elegance in that.
Yeah.
Well, how do we actually implement this backtracking magic? It sounds kind of tricky.
Yeah. So we can use recursion to our advantage here.
Okay.
Think of it as breaking down the problem into smaller, self-similar steps.
So we're essentially making a decision at each step.
Right.
Do we include this number in our current combination? Or do we skip it and move on to the next one?
Exactly.
It's like those choose-your-own-adventure books.
You're catching on quickly. And just like in those books, each choice leads us down a different path, creating a branching tree of possibilities.
This is making a lot of sense.
Yeah.
But I'm curious, how do we know when we've actually found a valid combination?
Yeah, that's a great question.
And how do we avoid getting stuck in an endless loop of recursion?
So that's where the concept of base cases comes in.
Okay.
A base case is like a safety net, a condition that tells our recursion when to stop.
Okay. Hit me with those base cases.
All right, so first, if our remaining sum is 0, bingo, we've hit the target precisely, and we've found a valid combination.
Nice.
We add this combination to our result list and celebrate.
All right, that makes perfect sense. What's the other base case?
The other scenario is if our remaining sum becomes negative. This means we've overshot the target.
Right.
No point in continuing down this path.
Yeah.
So we backtrack and explore a different branch.
I'm starting to see how backtracking is like a guided exploration.
Yeah.
Where we're constantly checking if we're on the right track.
Exactly.
And adjusting our course as needed. It's much smarter than just blindly trying every combination.
Exactly. By strategically pruning those dead-end paths, we save a ton of computational time and effort.
Right.
And believe me, your computer will thank you for it.
Okay, cool.
Yeah.
So I think I have a good grasp of this.
Awesome.
But let's dive a little deeper into some of the optimizations that we can use.
Okay, sounds good. Now that we've grasped the core idea behind backtracking, it's time to get even smarter.
Okay.
You know, like those seasoned detectives who can spot subtle clues that others might miss.
Ooh, I love a good detective analogy.
Yeah.
So what are these backtracking clues we should be on the lookout for?
Well, one powerful optimization involves sorting the input set of numbers before we even start exploring combinations.
Sorting. I'm not immediately seeing how that would speed up our search.
Right.
Help me connect the dots here.
Okay, so picture this. We're exploring a branch of our search tree.
Right.
Adding numbers as we go.
Right.
And suddenly, the current sum exceeds the target.
Oh, right. One of those dreaded dead ends we talked about earlier.
Exactly. But here's where sorting comes in handy.
Okay.
Because our numbers are now in order.
Right.
We know that any further numbers we add will only make the sum even larger.
Okay.
We're doomed.
So we can immediately backtrack and avoid wasting time exploring those doomed branches. That's brilliant.
Yeah.
Sorting gives us a way to spot those dead ends earlier.
Precisely. It's like having a shortcut in our maze.
Right.
And by pruning more branches, we make our backtracking algorithm even more efficient.
I'm starting to see how these optimizations are like adding turbochargers to our code. Absolutely. Small tweaks that make a big difference in performance.
And there's another optimization that plays nicely with sorting.
Okay.
Instead of considering all numbers from our starting index onwards, we can restrict ourselves to only those numbers that are less than or equal to the remaining sum.
Wait, so if our remaining sum is, say, 5,
Yeah.
we wouldn't even bother with numbers like 6, 7, or 8.
Exactly.
Because we know they'll instantly push us over the target.
You got it. By being selective about which numbers we consider at each step, we folder shrink the search space.
Gotcha.
Making our exploration even more focused.
It's like having a map that only shows the relevant paths in our maze. These optimizations really change how I visualize the whole backtracking process.
Yeah.
It's not just about blindly exploring every path. It's about making smart choices along the way.
That's the art of efficient algorithms, guiding the search towards promising paths and avoiding dead ends as early as possible.
It's all starting to click. By combining sorting with this limited choice strategy, we're essentially fine-tuning our backtracking engine for maximum performance.
Precisely. And these are just a couple of the many optimizations that can be applied to backtracking for the combination sum problem.
Right.
There are even more advanced techniques out there, but these foundational ones are a great place to start.
It's amazing how even a seemingly simple problem like finding combinations can lead to such a deep dive into algorithms and optimization.
It speaks to the beauty of computer science.
Yeah.
There's always more to discover,
Right.
more ways to refine and improve our solutions.
For sure.
But while Backtracks is a powerful tool, it's not the only approach to solving the combination sum problem.
Wait, there are other ways to crack this code?
Sure.
I'm all ears.
Okay.
What other secrets lie in our algorithmic toolbox?
Let's shift gears a bit and explore the world of dynamic programming.
Dynamic programming.
Yes.
I've heard whispers of its power. Something about breaking down a problem into smaller sub-problems.
You're on the right track.
Okay, my brain is ready for a new challenge.
Dynamic programming is all about solving a problem by building up solutions to smaller, overlapping sub-problems. And it turns out this approach fits the combination sum problem quite nicely.
Okay, I'm intrigued.
Yeah.
How would we apply dynamic programming to find these combinations? Paint me a picture.
Imagine creating a table
Okay.
where each entry represents a possible sum.
All right.
From 0 all the way up to our target sum.
So if our target sum was 7,
Yes.
our table would have entries for 0, 1, 2, 3, all the way to 7.
You got it. Now, each entry in this table will store a list of all the possible combinations of numbers that add up to that specific sum. It's like a master list of solutions.
Gotcha.
For every possible sum.
Okay, I'm starting to see the structure here.
Yeah.
But how do we actually fill in this table?
We start by initializing the entry for sum 0 with an empty list.
Right.
Because no numbers are needed to reach a sum of 0.
Makes sense.
Then we iteratively fill in the rest of the table, building upon the solutions we've already calculated.
So it's like we're constructing a building brick by brick.
Yes.
Using the previous levels as our foundation.
That's a perfect analogy. So for each number in our input set, we go through each entry in the table, starting from the number itself up to the target sum. If an entry already contains combinations, we know we found ways to reach that sum.
So we can leverage those existing combinations to create new ones for larger sums.
Exactly.
Like a chain reaction of solutions.
For example, if we're considering the number 2, and the entry for sum 5 already has some combinations, we can add 2 to each of those combinations to create new combinations for sum 7.
Ah, I see. We're building upon previous solutions to efficiently construct solutions for larger sums.
Exactly.
Avoiding redundant calculations along the way.
Yes.
Dynamic programming is like having a blueprint.
It is.
That guides us towards the final solution.
It's all about storing and reusing results. Making our algorithm smarter and more efficient.
So we've got these two powerful approaches. Backtracking, where we strategically explore a tree of possibilities,
Yeah.
and dynamic programming, where we construct the solution from the ground up using a table.
Right.
So having two different maps to navigate the same terrain.
And just like choosing the right map depends on the terrain.
Yeah.
Choosing the right algorithm depends on the problem.
Right.
Both backtracking and dynamic programming have their own strengths and weaknesses.
Okay, so backtracking is like our trusty compass and map, guiding us through the maze of possibilities.
Yeah.
But dynamic programming, it feels more like a satellite view.
Okay.
Giving us a bird's-eye perspective of the entire solution space.
That's a great way to put it.
Yeah.
Backtracking is often more intuitive and flexible,
Okay.
while dynamic programming can be incredibly efficient for problems with overlapping subproblems, like this one.
This is blowing my mind.
Yeah.
It's like having a whole arsenal of problem-solving weapons at our disposal,
It is.
each with its own unique powers.
Exactly.
Knowing which one to choose is half the battle.
Absolutely. And that's what makes the world of algorithms so exciting.
Yeah.
There's always more than one way to solve a problem.
Right.
And the journey of discovering these different approaches is as rewarding as the solution itself.
It's amazing how the same problem, that combination sum challenge, can be tackled from such different angles.
Yeah.
Backtracking dynamic programming, it's like having a whole toolkit of problem-solving strategies.
It's like being a coding chef. We've got our ingredients, the problem, and the data.
Right.
And we can choose which culinary techniques to use to create a delicious solution.
I love that analogy. But before we wrap up this deep dive,
Yes.
I have a feeling you've got one more trick up your sleeve.
I might.
You mentioned a final twist to the backtracking approach.
Ah, you remembered. Yes, there's a clever little optimization.
Okay.
We can sprinkle into our backtracking recipe.
Okay.
It's all about adding an early exit condition right at the beginning of our recursive function.
We talked about early exits before,
Yeah.
like when we hit a dead end and our sum goes over the target.
Right.
But this sounds different.
Yeah.
What's special about this early exit?
This one checks if the remaining target sum is already 0
Okay.
before we even start exploring any numbers.
Wait, wouldn't a 0 sum at the very beginning mean we haven't even started adding numbers yet?
Yeah, think about it this way.
Okay.
In backtracking, we're recursively calling the same function right. So we might reach a point deep down in those recursive calls where we've already found a combination that perfectly matches the target sum.
Ah, I see. So if a remaining sum is 0, we know we've already stumbled upon a valid combination.
Right.
And there's absolutely no need to keep exploring further down that branch.
Exactly.
It's like realizing we've already reached the exit of the maze.
This simple check can save a surprising amount of time and effort.
Right.
Especially in cases where there are multiple valid combinations.
Okay.
It prevents us from unnecessarily wandering down paths that have already led us to the solution.
It's like those choose-your-own-adventure books.
Yeah.
Where you can sometimes skip ahead if you've already found the winning ending.
That's a great way to put it. We're essentially telling our backtracking algorithm,
Okay.
hey, you already found a solution down this path, so you can relax now.
It's incredible how even these small optimizations can make such a difference.
They really do.
It's like finding those hidden shortcuts in a video game that let you speedrun to the finish line.
And just like in those games, knowing these shortcuts can elevate your coding skills to a whole new level.
This whole deep dive into the combination sum problem has been an absolute blast.
It has.
We've journeyed through the twists and turns of backtracking,
Yeah.
explored the elegant structure of dynamic programming,
Absolutely.
and discovered some seriously clever optimizations along the way.
I hope our listeners are feeling as energized about problem solving as we are.
Absolutely. And a huge thank you to you, our expert, for guiding us through this fascinating landscape of code.
It was my pleasure.
And to all our listeners, thank you for joining us on this adventure.
Yes. Thank
We
you.
hope you've learned something new,
Yes.
gained some coding inspiration, and maybe even learned a new way to solve the combination sum problem.
Don't forget to check out the show notes
Yes.
for links to resources,
Yeah.
code examples,
Right.
and all sorts of goodies to help you dive deeper into these concepts.
And until next time, keep those coding brains buzzing, explore those algorithms, and never stop optimizing your solutions.
Happy coding, everyone.